In order to understand the role that trigonometry and force components play in force diagrams, we need to observe what forces are doing to certain objects. This force is pulling up on the box. If the force is applied to the right, that means it's pulling the box to the right. Up to this point, we've only seen up and down, left and right forces. When we have an angled force, we cannot balance with another angled force. Instead, we look at the fact that this force pulls to the right and it pulls up. We're looking at horizontal and vertical forces at work. We need to pull this angled force apart into those two components, vertical and horizontal. Any angled force can be broken up into two parts. The parts are horizontal and vertical components. In this case, we have an angled force going up and to the right. We have a vertical component that goes or travels of magnitude of the overall distance in a vertical direction that vector traveled. The horizontal component has a magnitude that's equal to the horizontal distance that the vectors traveled. Ultimately, what it creates is a right triangle. The angled force will always be your hypotenuse, the vertical component will always be one leg, and the horizontal component will be the other leg. Knowing the measurement of the force and the angle, we can use our trig functions to calculate the two components. So if we are given that the angled force was 10 newtons and applied at an angle of 35 degrees, we could find either the vertical or horizontal component. All you need is one side and one angle of a triangle in order to solve for any other side. So we'll use SOHCAHTOA to decide which trig function to use. We're solving in this case for the vertical component first. That is our opposite side. The reference angle of 35 degrees is touching the horizontal, but it's opposite the vertical. The angled force is 10 newtons. The angled force is always our hypotenuse. It's always the longest force or longest side of the triangle, and it's always directly across from where that right triangle's right angle is located. So we have the opposite, we're looking for the opposite. We have the hypotenuse. That's so. Sine is the ratio of opposite over hypotenuse. So we use the trig function and the given angle, and then we use that trig ratio of opposite over hypotenuse. The opposite is unknown, so we put a variable in. The hypotenuse is known. It's 10 newtons. If we look at that trig ratio of x over 10, since the variable's up top, we're going to multiply both sides of this equation by our denominator, 10. That'll make it x on the right and 10 times sine of 35. If your calculator is in degree mode, not radian mode, you should get 5.7 newtons. Remember, include a unit on there. This value represents not just the side of a triangle, but the vertical component of an angled force. This is how much that angled force is pulling up. Let's look at how much that angled force is pulling to the right as well. So we're looking for the horizontal component, which in this case, based on our reference angle of 35 degrees, this is our adjacent side. It's the side that the angle is touching. The hypotenuse, we already know, it's 10 newtons. So we have adjacent and hypotenuse. So COA. CA is cosine, which is equal to adjacent over hypotenuse. So we start with cosine, which is our trig function, the given angle, and then it's CA, adjacent over hypotenuse. The adjacent is unknown, so we'll put a variable in, x, and our hypotenuse, 10 newtons, is known. Since in our trig ratio, which is x over 10, since our variable is in the numerator, we're going to multiply both sides by our denominator of 10. 10 times cosine of 35, if your calculator is in degree mode, is 8.2 newtons. I'm going to automatically label as I go. Every time I find a force or a force component, I'm going to put it right in my force diagram, because I may need to use that value or that magnitude in order to infer a balanced or unbalanced force. So this tells me that the force of 10 newtons at 35 degrees can be broken down into its parts, 5.7 newtons to the right and 8.2 newtons up. So once we've done this, the 10 Newton force is now represented by the two components. we can take away that 10 Newton force that's at an angle. We only will be looking at the vertical and horizontal components because we cannot balance angled forces, but we can balance or calculate net forces and accelerations using vertical and horizontal forces. Let's apply this to a full force diagram. Here we have an object of 2 kilograms mass that's being suspended by 2 ropes. The ropes make a 35-degree angle with the object. In a case like this, always start with a force diagram. So there's my object. Gravity is always present. We had 2 kilogram mass, so 9.8 times 2 gives me 19.6 newtons. And then we have 2 angled forces. They're tension forces because it's a rope. We're going to break that into a 35-degree angle, and we need to find our 2 components. Now, it didn't give us the angle of tension because that's what we're finding. Or sorry, the force of tension because that's what we're finding. And it didn't give us any of the components. If we know that the angles are equal, 35 degrees and 35 degrees, we can assume that both tension forces are pulling at the same amount. So that means that their vertical components, which would balance with our gravitational component, is equal. So the vertical component for Ft1, or the left tension force, and Ft2, the right tension force, would have to be equal. So I could divide 19.6 by 2 to get 9.8 newtons. All I need is an angle and a side to calculate any other force. They're asking me to find the tension force, which is the angled force, not the tension force's vertical or horizontal components. So if I'm given, or I inferred, the opposite side, and I'm solving for the horizontal, or sorry, the hypotenuse, opposite over hypotenuse is sine. So I'm going to use sine of the given angle equal to the trig ratio, opposite, which is 9.8, we inferred that, over hypotenuse, which is unknown. If the variable's down below, I'm going to switch places. The x is going to go where the sine of 35 is, and the sine of 35 is going to go where the x is. So I'm really doing 9.8 divided by sine of 35 degrees. If your calculator is in degree mode, you should get a tension force of 17.1 newtons. So that's the angled force. That's what they're looking for. This would be in a case if they're trying to find the tensile strength, or how many force, or how many newtons of force a rope would need to be in order to hold an object if it was being suspended, such as things for large-scale decorations, or even the tensile strength for bridges or suspension bridges.